Today, we will see how the spatial encoding is achieved. For spatial encoding, the gradient fields are used. There are three gradient fields: the slice select, phase encoding, and the frequency encoding gradients. When an RF pulse is applied to an object in the static field, the protons inside the object are excited, and MR signals are released as a result. We must first identify which signal is emitted from which area of the object in order to construct an image from these MR signals. The protons, on the other hand, are all placed in the same static magnetic field. As a result, all protons precess at the same Rameau frequency. As an outcome, the frequency of MR signals is the same. Therefore, we are unable to identify the corresponding origins of the signals in the object without further treatment. To tackle this difficulty, we use a position-dependent magnetic field, which causes protons in different locations to experience different amount of fields. As a result, their Rameau frequency vary from one location to the next, meaning that protons in different positions respond to different RF pulse frequencies. Thus, we can get position-dependent MR signals and figure out which part of the object generates which signal. Gradient magnetic fields are used to accomplish this. The addition of a gradient field to the static magnetic field causes Rameau precession frequency of the protons to differ from one position to another. Slice select, frequency encoding, and phase encoding gradients are the three kinds of gradient fields. The gradient fields are linearly dependent along each axis, and their orientations are perpendicular to one another. The slice select, frequency encoding, and phase encoding gradients are denoted by Gx, Gy, and Gg respectively, by their slopes in the field. Two waves can be distinguishable if frequencies are different. We can see here two different frequency waves, so we can easily figure out which one is which. If two waves have same frequency, we can distinguish if their phases are different. So in this figure, two waves have the same frequency. However, the phase is different. So we can distinguish these two waves. Rameau frequency of nuclear spins depend on the applied magnetic field, that is, omega equal gamma b. Only radio waves with the Rameau frequencies can resonate with nuclear spins. Nuclear spins emit MR signals through the NMR process, which are also radio waves with their own Rameau frequencies. As a result, we can infer that if we employ a magnetic field that is depending on position, we will be able to distinguish between MR signals coming from various positions. We can construct the MR image using these position-dependent signals. The fundamental concept of gradient fields is presented above. The position-dependent gradient magnetic field allows us to distinguish between MR signals because they differ in either frequency or phase. So for nuclear spins, if their Rameau frequencies are different, we can distinguish them. Even if the Rameau frequencies are the same, if their phases are different, then we can also distinguish them. So nuclear spin can be discriminated by their Rameau frequencies and phase. RF waves have a specific bandwidth. It is challenging to produce an RF wave using only one frequency. Consequently, RF waves used in MRI to excite nuclear spins also have a certain bandwidth. The figure depicts an RF wave with a central frequency of f0 and a bandwidth of delta f. So all radio waves have a certain bandwidth, which means that the RF wave consists of sum of different frequencies waves. This is the paper in Nature by October. October presented this paper which made the NMR to use MRI. So this paper is very important because this paper make an MRI possible. In this paper, October obtained the NMR signal which is located apart. Using the gradient field, he could distinguish MR signals from water sources that were located in two separate places, this place and that place. He could distinguish MR signals coming from this water source and that water source using gradient field. This accomplishment enabled the NMR technique to be used to generate MRI image. Let's see first the slice selection gradient. The total magnetic field, that is, the static field plus the gradient field, varies from point to point along the z-axis when the gradient field is applied. This is depicted in the right figure. The magnetic fields at the slices 1, 2, and 3 are all different. The field at position 3 here is the largest, while the field at position 1 is the smallest. The field is related to the Rameau frequency by omega equal gamma b. Because field intensity varies from point to point, the Rameau frequency varies as well. Only protons in the slice whose Rameau frequency matches the frequency of applied RF pulse can be excited by the pulse. So if we apply this gradient field, Gz, we can make position-dependent magnetic field. and at each point the protons has different Raman frequency, so we can discriminate. The slice selection gradient is applied along the static field B0, so G direction. In the figure, delta F represents the frequency bandwidth of the RF pulse. The thickness of the slice excited by this field, this radio field, is governed by applied RF pulse's frequency bandwidth, delta F. The slice thickness is what's called the slope of slice selection gradient influences slice thickness as well. So slope influences the slice thickness as well. The slice thickness decreases as the slope of the slice selection gradient increases at the fixed bandwidth of RF pulse. So if the slice is steeper, then image thickness becomes thinner. If the slice slope of the slice selection gradient is not this steeper, then image thickness will become thick. The total magnetic field at G position is static field plus the slope times the position C. The protons and the corresponding slice process with the following Raman frequency. Raman frequency is given by gamma B. So just put the total magnetic field Bz here, then we can get the Raman frequency at that position. If we differentiate this equation, we can get this equation. This is the relation between RF pulse's angular frequency bandwidth and the slice thickness. If we use the relationship omega equal to pi f, so omega equal to pi f, so we can put this here, and then the slice thickness is expressed by this expression. So according to this equation, slice thickness is inversely proportional to slope of the slice selection gradient. So it's easy, right? So we have a steeper slope, then we can have a thin image thickness. Okay. So if you use the RF pulse with the bandwidth f, okay, and then we also have gradient field. Then in this region, the protons in this region can be resonated by this RF pulse. In other area, the protons cannot be resonated because the frequency of RF pulse does not match with the Raman frequency. And the slice thickness is given by this relation, and the slice thickness is inversely proportional to the slope of the slice selection gradient. And delta F is also sometimes we can change, but if we fix this bandwidth, then slice thickness is linearly inversely dependent on the slope of the slice selection gradient. Now we choose the image thickness, and the image plane is fixed by the slice selection gradient. Even if the slice selection gradient choose a slice with a specific slice thickness, we cannot distinguish which MR signals come from which portions of the slice. The protons in the slice feels the same magnetic field, and thus the protons number frequencies are the same, so we cannot distinguish MR signals from which portion has which signal. We cannot identify them. So protons in the slice has the same normal frequency, and the MR signal they emit has the same frequency, so we cannot distinguish the MR signals which comes from which portion of the slice. We cannot distinguish them. Gradients of phase and the frequency encoding can be used to solve this problem. Voxels, which stand for volume elements, are used to divide the slice. If the slice thickness is thin enough, this voxel might be regarded as fixture element. So, as fixture element, if thickness is very thin, then we can take voxel instead of voxel. We can be regarded as pixel. The MR signal from each pixel should be different in order to distinguish all of the pixels. The frequency and the phase are the two characteristics that distinguish the wave. We already mentioned this. We can distinguish the wave by their frequency and phase. The frequencies are different, then we can distinguish them. Even if the frequency of waves are the same, but the phase are different, we can distinguish them. So if the frequencies of two waves differ, they are different waves. Even if two waves have the same frequency, we can tell them apart if their phases are different. As a result of the phase and frequency encoding gradients, the MR signal from each pixel can be distinguished. The frequency encoding gradient produces a frequency difference in the MR signal from each pixel, whereas the phase encoding gradients create phase difference across pixels. Let us consider a simple 3x3 pixel image here, shown in the figure. Without phase encoding and the frequency encoding gradient, 9 pixels, the protons in the 9 pixel the same normal frequency and the same phase, so we cannot distinguish them. Now across the y-axis, this axis, the phase encoding gradient is applied. So this kind of slope. Okay. The normalization vector of pixels in the middle row does not change their normal frequency as a result of this gradient field, because gradient field is 0 here. So normal frequency in the center row does not change. The normalization vectors of pixels in the upper row, on the other hand, process faster than those in the middle row, because gradient field is plus. So upper row, the precession frequency is faster than that in the middle row. Normalization vectors of pixels in the lower row, on the other hand, here, -1. So process slower than those pixels in the middle row. So precession frequency in this row is smaller than that in the middle row. Okay. The gradient field causes the normalization vectors of pixels in different rows to process at different frequencies as a result of this field. If the gradient field is switched off at this moment, the normalization vector of each pixel processes at the same normal frequency once again. However, the normalization vectors of pixels in different rows have now different phase difference. You can see here the phase is different, right? The starting point of the precession is different. We'll call this phase difference theta. Then we can now distinguish the pixels in different rows due to phase difference. However, the pixels in the same row remain undistinguishable. It's the same, so we cannot distinguish them. The phase encoding gradient causes the pixels in different rows to have different phases. The frequency of the pixels in the same column is still the same. So this column, the same frequency. So we employ a gradient of frequency encoding along the x-axis to discriminate between pixels in the same column. So in this x direction, we apply this kind of gradient field. So then normalization factor at this column process faster, I speak for plus, right? Faster than that of this column. The frequencies of protons in this column does not change due to this gradient field because there's zero, right? But the left one, this one, the precession frequency is lower than that in this column because it's minus gradient field. Therefore, Rameau frequency in 3 columns are different. So margin vectors of pixels in the different columns process at different Rameau frequencies. As a result, the normalization vectors of all the pixels have different Rameau frequency or phase values. So we can discriminate all pixels. The frequency and the phase of the MR signals for each pixel are shown in the figure below. The letter A, B, and C and so on in this figure denote pixel signal intensity. So it's A, B, C, or D. The echo signal is represented by sinc function. This is called sinc function. You can see in this figure that each pixel signal has unique value in either the Rameau frequency or phase. Okay. If we have only slice selection gradient, then the signal for all pixels are the same frequency and the same phase. No phase in all pixels, right? So we cannot discriminate the signals. Once we apply phase encoding gradient, then we can create phase difference between each law. Okay. So here, upper row, phase is plus zeta by this phase encoding gradient. So no phase in the middle, and minus zeta in the row, in this row. So by this phase encoding gradient, phase difference is generated. But still we cannot discriminate the signals in the same row. Same way. Now if we apply frequency encoding gradient in the x direction, this is y direction, then this column, the Rameau frequency is omega minus because we apply the negative slope. This is positive slope. So this is 0. So in the middle column, the field is 0, so Raman policy does not change, omega, but in this column, Raman policy increased due to the plus gradient field, plus. So we can see the signals in pixels. They are all different, either the Raman frequency or phase. So all different. We can see the signals are all different, either frequency or phase. So we can discriminate the signals of all pixels. Still, we have a problem because we obtain the data after completing the process depicted in the previous slides. However, this signal is a mixture of MR signals from all of the pixels. We cannot measure the signals coming from each pixel. We just measure the signal coming from all pixels together. Right? So even if we use Fourier analysis approach to manipulate this data, we don't have enough information to identify the signal of each pixel, its frequency and phase. To solve this problem, we repeat the process depicted in the previous slide, adjusting the phase encoding gradient each time. By doing this, the phase of each row is changed sequentially, at least for the same number of rows. As a result, in order to get the signal for 3x3 image, we must apply at least 3 different phase encoding gradients. Okay. To begin, we get the signal without use of a phase encoding gradient. This way. Second, the phase encoding gradient produces 120 phase difference between rows. In this case. And third, there's now 240 degrees phase difference between successive rows. The frequency and phase of all line pixels are computed using these 3 signals. The Fourier analysis technique is used to do this. This Fourier analysis approach determines the amplitude of the RF signal for each pixel and is utilized for imaging. Now let's compare data taken process between MRI and the CT imaging. The data taking process in these two imaging machines are nearly the same. So we can see what kind of techniques are used in the CT imaging. The transmitted X-ray intensity recorded by film or CCD is used to generate X-ray image. So we put here film or CCD, and X-ray is transmitted through the material and can be detected here by detector For imaging, we use the film or CCD to detect the intensity of transmitted X-ray. Every material observes X-rays differently. Consequently, the X-ray image is created using these material-dependent transmitted X-ray intensities. The absorption coefficient of the material is defined as this equation. Here, mu is the material's absorption coefficient, and x is the thickness of the material, and I0 is the intensity of instant X-ray, and I is the transmitted X-ray intensity. Okay, so X-ray intensity of I0 is transmitted through a certain material of sequence X, and sum of energy is observed by this material, and a smaller intensity than that of instant X-ray is detected here. Okay. This material-dependent X-ray absorption is used in the X-ray CT. CT is called the computerized tomography. The grayscale is formed using the absorption coefficient of the pixels in the image plane, and the image is then constructed. X-ray CT data acquisition process is similar to the MRI process. For image construction in the CT, the absorption coefficient of each pixel is utilized. We must determine one 10,000 absorption coefficient of 10,000 pixel image as shown in the figure below, which is 100 by 100 pixel image. You can see here we divide image plane by 10,000 pixels. So in this direction 100, and this is 100, so we have 10,000 pixels. So we have to obtain the absorption coefficient of 10,000 pixels. Then we can make an image. So in this case, we use the 100 detectors here to measure the X-ray intensity coming from here. Okay, so that's one detector. We have 100 detectors here. So in this case, but if 100 X-ray detectors are used, we can only have 100 data when the X-ray passes the image plane. So, for one scan of X-ray, we can have 100 data, right? Each detector measures the X-ray intensity that remains after X-ray has passed through the various organs, bones, and the tissues it encounters along the path. So X-ray emits various kinds of organs, bones, and tissues passing through this line. Okay. So if intensity of instant X-ray is I, 0. Then detector here measure the X-ray intensity, I0 exponential, this pixel coefficient mu11, mu12, mu13, and mu1m. We assume that the thickness of pixel is the same, delta x. Okay. So this detector measures the transmitted X-ray intensity, but this X-ray passes through various materials, organs, bones, and tissues. So we cannot get the absorption coefficient from this data. Let's put together. So we cannot discriminate the absorption coefficient of each pixels. Because of this, we are unable to distinguish between absorption coefficient among all pixels the X-ray encounters along its path using this data. So we have just 100 data for one scan of X-ray through the image plane, but we have determined the 10,000 absorption coefficient of pixels. So data is not sufficient to figure out the absorption coefficient of all pixels. So since we only have 100 data for a single X-ray scan through the image plane, we need more information, more data to determine the absorption coefficient of 10,000 pixels. As a result, we scan the image plane 100 times while also rotating the X-ray source 100 times. So we need 100 more X-ray scans. For each X-ray scan, we can have 100 data. So if we do the X-ray scan 100 times, then 100 times, that means we have 10,000 data. So we can figure out absorption coefficients of 10,000 pixels, right? The rotation angle on X-ray is 180 degree divided by 100 degrees, about 1.8 degree each. So for first scan, we do not rotate the X-ray source, and next step, we rotate X-ray source 1.8 degree, and then take data, and next 1.8 degree more, so total 3.6 degree rotate, and then have data. So in this way, we can have 100 scans. Then the number of data we have is 10,000. So we have to figure out 10,000 absorption coefficient of pixels. Now we have 10,000 data, so we can figure out the all absorption coefficient. So we can obtain enough information in this way to determine the absorption coefficient for 10,000 pixels. To find absorption coefficient of 10,000 pixels, we must solve 10,000 coupled first order equations, and this requires a computer. Hence, we refer to the CT as computed tomography. In this CT, we use X-ray, but people do not like X-ray, so X-ray was omitted. So we call just CT, computed tomography. The function of computer is just a calculation of the absorption coefficient from 10,000 data. But the important function is given by X-ray, but people don't like X-ray, so in the name of this machine, X-ray was omitted, so we call just a CT. We must rotate the X-ray source by 180 divided by n degrees each time, and collect the n times if the image plane is made up of n by n pixels. We also require n X-ray detectors to be placed behind the patient in this case. So these detectors, right? So it's ring detectors. So in this way, the CT obtained the absorption coefficient of each pixel, and the image can be constructed by this absorption coefficient. In MRI, to obtain sufficient data to distinguish the signal frequency and phase from each pixel, we use the phase encoding process, which is very similar to the process we described for the X-ray CT. For n by n pixel image, we need n different phase encoding steps. The number of phase encoding gradients should match the number of image columns. The number of phase encoding steps should be n if the image is divided into n by n pixels. N is typically used between 64 and 512. If you use larger number here, then the image resolution is improving. So if you use 512, we have high resolution image than 64, right? Usually we use n is 256. So if we use n equal 256, then the application of 256 different phase gradients is required. The smallest phase gradient or step size, delta Gy and Cy, causes phase difference of pi of ny between neighboring pixels. So here, if we use this gradient, the smallest gradient, then phase difference between two adjacent pixels is pi of ny, and the phase difference between center and the edge is pi. The same thing here, just minus pi here. So phase difference between center and this edge is pi also. As the phase gradient increases to this maximum gradient, then this difference increases to value of pi. So in this case, the phase difference between adjacent pixel is pi. So we explain again here. No phase encoding gradient, then no phase shift between any of pixel columns. A first step, the smallest gradient, then linear phase shift from 0 to 360 degrees is created a closed image. So from here to here, we have 360 phase difference. A shift of 360 divided by ny, for ny equal 256 this degrees exists between adjacent pixel columns. Okay. Now, next step, twice of this one, twice the smallest slope, then linear phase shift closed image is expanded to twice, right? So 720 degrees from here to there, here. So the phase shift between adjacent pixel columns are also doubled. So just doubled compared to this. The last step, the largest slope. Many phase cycles encompass the entire image. Adjacent pixel columns differ in phase by 180 degrees. So adjacent pixels here and here. So phase difference between these two columns is pi. Okay. Well, in this way, we continue 256 times by changing the slope of the phase encoding gradients. Then we can have enough data to discriminate the frequency and phase of the all pixels. In the spinnacle pole sequence, the order in which gradient fields are applied is shown in the figure here. When the 90 degree and the 180 degree pulse are turned on, the slice selection gradient is applied first. So at the moment of the 90 degree pulse and 180 degree pulse, slice selection gradient is applied. Then between turning on the 180-degree pulse and detecting the echo signal, so here between here and here, the phase encoding gradient Gy is applied. So phase encoding gradient is applied. Finally, the frequency encoding gradient Gx is applied simultaneously with the echo signal detection. At this moment, we apply frequency encoding gradient, then we can get the echo signal. As a result, the frequency encoding gradient is usually referred to as the readout gradient. So at this moment, the signals is obtained. So we call this frequency encoding gradient as readout gradient. We must go through this process n times by altering the phase encoding steps. So this phase encoding steps. For example, we have image of 256 by 256. Then we have to go through this process 256 times. After using the Fourier transform technique to distinguish the signal intensities of each pixel, the grayscale MRI image is constructed using these signal intensities of pixels. Let's assume that for 3x5 image, we get the signal intensity value determined like this. Then using this value, we use the grayscale, then we can get the MR image. Each pixel signal intensity is related to its relaxation times. The bright pixel in the T1 weighted image reflects short T1 relaxation time there. On the other hand, the bright pixel in the T2 weighted image reflects a long T2 relaxation time at that pixel. So we can have finally get the MR image from the data. We can use the Fourier transform using this data, and then we can get the intensity of each pixel, and using this intensity of each pixel, we can get MR image. Now see some example regarding we discussed so far. Example 1, as gradient for slide selection, 10 millitesla per meter gradient field was used. The RF pulse has 2 kilohertz bandwidth. What is the image thickness in this example? We have expression, this expression, so we can easily get the slice thickness was 4.7 millimeter. Next example, an RF pulse has 1 kilohertz bandwidth. Determine the slice selection gradient for these 4 slices with 5 meter thickness. So we want to obtain image of 5 millimeter thickness. In that case, what slice selection gradient we have to use? So slope can be obtained this relation. The slice selection gradient's maximum slope is 10 millitesla per meter. What is the slice thickness if RF pulse's minimum bandwidth is 400 Hz? So maximum slope for slice selection is given, and the minimum bandwidth is given. So we can have the slice thickness, this value. I want to omit. Okay, let's just do this example. In a 1.5 MRI, water containing samples at the 0 centimeter and at x 2 centimeter are placed. This is similar to the Rotorber's experiment. Rotorber obtained MR images from water sources located at different positions. So this is similar to the Rotorber's experiment, right? So x centimeter, 0 centimeter, and 2 centimeter, the water contained samples are located, right? So we used 1 Gauss per centimeter gradient field along the x-axis to detect RFID signal. Calculate the resonance frequency difference between two positions. The position-dependent field is given by V0 and GXX. Hence, the normal frequency is given by this expression. As a result, the resonance frequency difference can be calculated as follows. So x1 minus x2 is position difference between two samples as 2 centimeter, and gx we used 1 Gauss per centimeter. So you can get resonance frequency difference 8.52 kilohertz. I'll omit this example and also this example. The last example, the gradient field is constructed using anti-harmonic coil. This is anti-harmonic coil. Coils are placed 1 meter apart. The distance between coil is 1 meter. At core center, each coil produces 3 Gauss. So there's core center here. Or each coil produces 30 Gauss. So for this coil, the direction of field produced is this direction, and here, so field current direction are different. So at this center here, direction of field is in this direction. Determine gradient field slope. Two coils current flow in opposite directions. The field at the intersection of two coils here, P point, zeroes out. So at this point, sum of fields will be 0. So at the center of coils, yeah, and there, fields have opposite directions. Okay, opposite directions. Thus, gradient slope can be determined as follows. There's distance between two coils and difference between fields. So we can have the slope of the gradient field. That's 0.6 Gauss per centimeter.